then set S1 to 1. Reset means set to 0. Set means make it 1. Remember that. Reset 0, set 1. So to answer this problem, first you have to think for a second, what's the characteristic of a binary number that tells us if that number is even or odd? Well, think of a decimal number. What tells us if it's even or odd? If it's divisible by 2. So now binary numbers, think of a binary number, what's the least significant bit? It's a number of ones. If it has no ones, it means it's divisible by 2. So we say here, if it's an even number, the least significant bit's 0. If it's an odd number, the least significant bit's 1. Does it always work? It always works. Why? Because it has no ones as a factor of that number. That's what so yeah, we keep mentioning binary numbers, but that's how we design circuits, and we need to have these insights. So how can we determine if the contents, right, of S0 is even or odd? We want to just look at the least significant bit. How do we do that? Mask away everything else and then check it. Sound easy enough? Yeah. So here is the procedural way, and here's a cool way. Okay, so here's a procedural way. So what we can do is, like I said, mask off everything except the least significant bit. So here's our mask. And suppose I AND with that mask. What am I left with after I AND? What's left in T1? Only the which bit? Least significant bit. Great. Then what? I can test it, like I said. It's a skip condition, right? Right? If the least significant bit is a 1, it means it's odd. Right? So if the least significant bit turned out to be a 0, because everything else in the register is a 0, so I'm just looking at the least significant bit. If it's equal to 0, then it must have been an even number. I go to even. I'm going to write a 0 into S1. Why? Because it said that to reset it. If that condition is not true, the bit can only have 2 values. Either it's a 0 or 1, so it must have been a 1, which meant what? Odd. Under odd condition, I want to set S1 to 1, so I do that by this. What is the semantics of this instruction? I know you guys know it, just keep me awake. It's not. Anybody, raise your hand. 1 point extra credit. Go ahead, you got it.
S1 becomes 1. You add 0 plus 1.
Correct, but give me the semantics step by step for this. And you can email me your name and I'll give you the point. What does it say? What is this?
Add 0, add the integer 1.
Correct. This is an immediate value.
Add it to the register 0.
Which has a value of?
0.
And?
Store it and registers.
Excellent. So at this point, S1 gets set to 1 and we're done, right, with that case? Why do we have the jump here? Because we don't want to undo what we just did. We have to skip. I think this program will work. You can put in, I encourage you, scrape this code, scrape this text, put it in Mars, and try it, and try putting some different values of S0 here, and odds and evens, and gigantic numbers and small numbers. You can see it works. And you can step through it and see why, and see the jump happening. You can also see the AND happening. Where do you see it? In the register window on the right side, you should be able to see step by step. You do step mode, watch the bits disappear, and okay. Here's a concise solution. Can I do it in one instruction? This is efficiency, right? You can write this, but that was a ton of time and energy relative to this. They want to explain the semantics of that last instruction.
Which instruction are we talking about?
Last one on this page. Concise one. Yeah.
If S0 is 1, then it's going to store a 1 in S1.
And that is correct. And how does that?
It's doing the AND between 1, and if there's a 1 in there, then it'll come out as 1. If there's a 0, it'll come out as 0.
So S0 has a bunch of bits in it. 1, 0, 1, 0, 0, 1. And then you ANDed it with an immediate value of 1. What does 1 look like as 32 bits? All zeros and 1, 1, right? So we know AND is 0 sensitive. So your output is going to be either one or two choices. It's going to be this if that happened to be a 1. See? Or if this happened to be a 0, your output is 0. So the output is into S1, which what was asked for in the specification. S1 is 0 if you started with the 0. S1 is 1 if you started with the 1. So S1 is set to 1 if it's odd. If S0 is odd, S1 is set to 1, right? S1 is my output, right? Down here is the next, right? Is the output. See, if I AND this and this, I AND these together, 1 and 1 is 1. If it's a 0, I don't care what these other things are. It's actually don't care condition because they get masked away. See? So this is a 0. It comes out as 0, which meant that it was an even number. Yes, it was an even number. You do it in one instruction. Right? Are both correct? They're totally both correct. What's the difference? If you're talking about efficiency in terms of execution time, this is going to take a lot less execution time because we have that instruction plus a whole bunch of other ones here. What about energy? Less energy? What about space on disk? It's actually even lower static instruction count. Okay, no jumping. Easier to debug, easier to maintain. But probably we need to give a little comment here. You're going to say, well, I totally know what it is. I'm sure you do. But then the next guy, right, is going to get this code and like, we call them one-liners. And it's like, if you write code, which I don't, but I've taken enough classes, right, that it becomes like a point of pride. Like I can write this thing in one line of code, right? And these complicated programs. Any C programmers here, like do for pay or anything? Sometimes, right, you can do even conditional expressions and you AND things together and you get a 1 or 0 times something else, and then this is the assembly version of doing it in one line. Yeah. Some languages are really amazing. There's one. Anybody programming literally stands for a programming language. It's a mathematical based one. But the cool thing about APL is you don't have to have loops. And actually, I learned on that first. And you can take a whole matrix and you can multiply another matrix times another matrix just with one instruction. Or you can take a vector and a matrix. You can organize a list with an iota and make a string of values without making loops. So different languages have different expressiveness. APL is really amazing. You can express things one-liner really compact and no looping. Looping makes us dizzy, actually. We don't like loops, but depends on your machine. You may end up with loops anyway. There's a very cool one just to tie a bow on it. If you go here, you can see. You can do Conway's Game of Life. What's Conway's Game of Life? You can do it in one line of APL code. It's a whole. This is Conway's Game of Life, right? There's a video. This is where you start with a matrix, and it can be like bacteria. There's a lot of models, right? But you need food to propagate, and then you can replicate. When you watch these things create, it's called cellular automata over time here. We won't watch the video, but this is just and you can set different parameters. You have to have a certain amount of energy to do the next thing, and these things grow, and it becomes it's just like propagation in an ecosystem. The cool thing is that you can write this in C, and the C code is about 4 pages, right? This is the cool thing. If you do this in APL, properly. One line. Yeah, okay. So this is a one-line program. So each one of these is a matrix, and actually what he's doing is getting the maximum matrix, seeing if it's a member of this, is there an element of this that's a member? Kind of cool stuff, right? Okay, something to look forward to if you think it's If you hate C, it could be worse, right? It could be worse. If you learn that first, then everything else seems nothing, right? Okay, so everybody good with this one? This is a good question because it makes us think about binary representation. What do bits mean? It helps us to translate from a specification to some design, whether it's assembly language or hardware, and we're going to do the hardware very soon, but also helps us to do trade-offs. See, there's more than one way. So how do these instructions look in memory and how are they encoded? Good question. Since they're I format, right, we have some format here, right? So let's take a look at this one. Here's a R format, and here is an I format. Since I format is going to have a constant, R format is going to have RS, RT, and RD. We haven't used shift amount, but we're going to very soon. So if you're given these 3 assembly language instructions, here's the semantics. They ask you for the instruction format, the same process. Look up in the table. Since it's R format always has the op 0. Well, where do we get the function? The function is contained in the func field. This is in the testing reference sheet. Let's show you. So and, it's register and, not immediate and. What's a register and opcode? So it's and, right? Not add. So and 024. 0 for op, 24 for funct. Sometimes they say funct, sometimes they say funk. Yeah, so we're good with that. What about RS, RT, and RD? Where's RD? T0, see it? T0 is 8, 9, 10. What about immediate mode? Excuse me. Immediate mode has an I format. So here we have and immediate from the table, right, is 0D. Zero D or 08? Or, sorry, ORI. I gave this in a minute. So here's ORI. ORI is 0D. Let's see. Can you go both ways? Yeah, it's a one-to-one mapping. The machine gets the sequence of bits. The machine knows it's ORI. If you're a human and you see ORI, you know the machine bit encoding. You can go either way, right? So what was ORI? 0D. Good. What's funct? It's a don't care condition. And here we have RS and RT. So let's look at the shift instructions. Again, we did shift left logical already. That was taking the bits and shifting them by the amount. Now let's do shift right. There's 2 versions of shift right. It gets the sign, and it's a positive or negative value. So shift right, we shift, when we're shifting, we always shift to 0 in. That's the definition of shift. If there's rotate, you actually go in a loop, and whatever comes out gets moved back in. That's rotate instruction. I don't ask you guys that, we just do shift. That's enough for this class. But another class you may do rotate, especially if you're interfacing with an embedded system. So shift right logical has similar semantics to shift left logical, the 0 comes in. But when we're shifting right, we're going to see when you have a sign value, the sign is the most significant bit, and we'll give you on the next slide, but that gives us a choice. If we want to keep the sign, if it's a negative number, we don't want to overwrite it with a 0 for that bit, because what we did is we changed the sign from negative to positive. If you want to maintain the sign, you want to use arithmetic shift. Arithmetic shift says not all bits have the same meaning. Logical, they're just bits. But arithmetic means it's an arithmetic representation. Arithmetic representation means that most significant bit is a sign, and we'll show that. So we know this already about multiply. I even covered divide, all right? And that's why I think it's a fair question on the exam, because we talked a lot about it, shifting and what it means, but that's okay. So the question is, if we're going to shift left, you're multiplying by 2. What about right? I did an example, divide by 2. Any number system, whether it's decimal or binary. Here we always do binary. All right, if it's decimal shift, it's going to be multiply, go right, divide by 10. If you go to the left, it's going to multiply by 10, because each digit is weighted by a factor of 10. Keep that in mind. So we'll see some examples. Here's an example to shift all the bits in a word right or left. What's the amount of shift? Here is a shift amount. The shift amount goes into this field. See SA. Shift amount. Sometimes they say SA, some data sheets, and other ones say SAMT, or they use SH, SHAMT, shift amount. That's the number 8. Why is the number 8? Because this instruction had 8. Here the shift amount would be 2 if I wrote the bit sequence for that, but this is the bit sequence for this instruction. The shift amount is 8. What about the rest of the instruction? Well, the opcode, SLL, is actually 0 for the op and 0 for the func. Let's take a look. That came from data sheet. SLL, shift left logical. 0 for the opcode and 0 for func. All right, good. What about the other fields? Other fields are registers. Where's RS and RT? Well, they do RT and RD. That's how they code it. So we'll see some examples on the next slide. But this is shifting left by 8. This is shifting left by 2. And this can convert from word offset to byte offset. We already saw many examples. If you have an index in your program as A sub 300, we had to convert that from index to byte address, because memory is byte addressable. Byte offset at 1200, we have to multiply 300 by 4. You can have the value of 300, shift it left 2 bits, multiply by 4. And we can add the base address to that, which is where the array starts at, and then we get the value in memory and get the address from that. That gets loaded into a register, which is actually loading the value that we wanted to access from memory in the array. So let's put that to work. Here's a C program with arrayed values, and we want to access this in memory, and we have also some other specification, making it more interesting. We did even and odd. Now we're going to put it to work. So suppose array elements with the even index, we desire to increment them by 1. So we're stepping through the array, only the even elements. For those with an odd index, we want to decrement. So if it's an even index, we add 1 to the value. If it's an odd index, we decrement it by 1. So this is one version of code that does that. More than one way to write this even, but here's a specification in a high-level language, C language, just because it's easy for humans to read, a little bit easier than APL. Yeah, it could be worse. Look on the bright side. There's an integer array with 20 elements. Question, how many bytes in memory does that occupy?
80.
Yeah, 80. See? It's good. So it's 20 elements, but each element's 4. Now C is a little bit tricky on this stuff too, which actually is always a confusion, right? Does it count 0 or not? I'm not going to be too picky on that. But, we have to input the values of A, so that's syscall, but I'm not going to worry about that. But then we get to the loop. Oh, actually it's C. The input is syscall, but here's some scanf, right? Scanf. Then we get to the loop. It goes from 0 to 19 inclusive. It's the first 20 elements. If it's divisible by 2, okay, it means it's even, then we want to add 1 to the contents. Else, if it was not divisible by 2, right, so we're going to get a 1 here. It's a mod, right? This is a mod. If the number is 1 that results from this expression, then we want to subtract 1. So what's taught is a MIPS assembly language program to perform the above function if the address of the first element of A is contained in S0. So address of first element of A is S0. So the base address, right, is another way of saying the base address of array A is in S0. So here's one version of code. There's many choices, but we should be able to step through this and see how this works and be able to create something like this. First we have to initialize. We have some index in our code that's going to be moving through the array A. So that's index I gets set to 0. Where that happened in the C code right here. See, I got set to 0. Doing the same thing here. So t0 is the variable I. What's next? Upper limit is t1. Then what? We're going to have a mask, because we're going to determine even or odd. We need a mask value of 1. Okay. And that's going to be used down here. See this t7? When we do the AND. So this is ANDing with a mask of 1. Can you do AND immediate? Yes, you can. This is just showing one way to do it with setting a constant for 1 as a mask. The way I set up this loop is I don't enter the loop unless the condition is true. What's the condition? If t0 and t1 are equal, initially 0 and 20 not equal, right? But when these two values become equal, I'm going to increment I every time. When it gets to 20, I stop. Why? Because this went to 19 inclusive. When it gets to 20, time to stop. How do we stop? We branch out. We break out of the loop. Go to exit. What's next? So then we have to convert this index, which is t0, from word to byte. So multiply by 2. Now it's the byte offset. But how do we get the address? We add the offset to the base. The base is in S0 as a given. Okay. Now we have an address in T2. Let me say it again. T2 is an address. Does everybody see that? It's not a value. How do we get the value? We have to load it from memory because that's where the data is. So I've already calculated the address plus the offset. I'm going to use a 0 offset relative to the T2, which contains this offset address of S0, which is the base of this array, plus T2, which has already been converted from word to byte. Good.
So is there a reason that they use add immediate instead of load immediate?
Where?
In the first key step?
Just showing another way to do it.
So there's no speed difference or anything? Is what you're saying?
Well, actually, if you write load immediate, it gets converted to this, and you can try it. Try it in Mars. So it's actually load immediate. It's a convenience for the programmer, because actually this is not as. This looks a little more cryptic. Yeah. So you can type load immediate. It will get. If you look at what code actually gets created, is this machine instruction. They are interchangeable. What's next? We're going to branch. No, first we're going to test, right? So then we have to mask, right? So we took the mask, and we got the value from memory, which is a sub I in this case, and we apply the mask to it. The masked value goes into T4. So T4 contains 31 zeros, and the last bit, least significant bit, is either a 0 or 1. How do you know? Well, it depends on what the original value was in memory. But I can use that to figure out if it's even or odd, which I'm going to do. So if that register contains all zeros, which means the first 31 plus the last, I know it's an even number. If not, I don't take the branch. It means it must have been odd. According to semantics, what do we want to do? If it's odd, decrement by 1. So the value that I started with, all right, T3, this is before the mask. See, before the mask was T3. So now this is the value before the mask. I subtract 1 from it.
Could you have used the and immediate instead?
Yes, I mentioned that at the beginning. Yeah, no worries. You can use and immediate. This is just showing setting a constant for mask. Yeah. Then what? Since we have an odd case, I want to jump over the even case, so I don't do both because just negate each other. Then what? Even case says what? If you had took this branch, you're going to add 1 to T3. Is T3 the masked value or the unmasked value of the variable? Masked or unmasked? T3. Well, T3 is loaded here. That's the value of a sub I. In this case, a sub 0 because the first time through. And the mask gets applied and it gets stored into T4. So T3 is masked or unmasked? Unmasked. Okay. So then what? The program said add to the value, right? We want to decrement those values. So that's why, the reason I'm pointing this out, just so I think if you understand this and you get what's going on. We want to add 1 to the add 1 to T3, not T4. because T4 is just either 0 or 1. T3 is whatever AI is. Are we good? Then what? Got to write that back out to memory. Why? Because this isn't a register. We've added 1 to A sub I, but that's inside the processor. Where's A sub I? By definition, A sub I is in our abstraction. Which component? Which chip? We held it in our hand. A sub I is always, it's always in the memory chip. Where's T3? Always in our abstraction. It's always in the processor. Okay, so we got to store. So you can say, well, I did the add, but if you didn't write that, I think it's like 1 point off, right? Because yeah, you added it, but you didn't do what they wanted. They wanted to update A3. They didn't want to just like add it and then forget about it. All right. Okay. So what's next? We have to increment I. And then what? Here is an unconditional jump. Why? Because I put the branch at the beginning. Because I don't want to enter the loop unless the condition is valid. You can do either way. But here I'm checking it at the beginning, and then I don't go in there unless I is not equal to the limit. It's a limit in this case. And the limit's 19, but 20. When it gets equal to 20, it's time to quit. See? When it's equal to 20, that was a 20 is a T1. So when I, which is T0, equals T1, T1 was 20. T1 has never changed in this program. So when it becomes a 20, it's time to quit. Because the same thing that happened here. I keeps getting incremented every time. When it gets to 20, so everybody see the abstraction. You have processor and memory. Some elements are in processor, which are registers. Some are in memory, which is array elements. The bits are loaded. They need a load word because the array is out in memory. Why? Because the operations occur inside the processor. That's its job. There's no circuits inside the memory. It's a research question to put some there, but that's an issue, separate issue. And then once we get the data in, bits have meaning. That's the point. Bits have meaning. The least significant bit in this case is relevant to this problem, telling if it's even or odd. We can test that. But we can't test an individual bit. We have to mask off everything and compare if the whole thing is 0 or 1 at that point. There's a question. Yeah.
Yeah, I was going to ask, what was the 0 in the same word in load word?
Can you say which, how?
In load word.
Load word.
The index.
Index, oh. So the offset is 0. Because we've calculated, in this first instruction, we've converted from the index I to the byte offset by multiplying by 4, and then we add the base. So already in T2 is the exact address of where the A sub I is. So therefore, I don't need to have any offset. It's offset is 0. Well, 4 per element. So it's actually 4 times I. But you can't put 4 times I here because this has to be a number. It's a constant. How do we know this is a constant? Because we look back, actually this is great. We're ready to see it. We saw it over here. What the machine actually executes for load word, you can use decimal or not. But anyway, load word is 16 bits a constant. It can't be I times 4. There's no way for the machine to handle that. It has to be a number, a constant. So how do we convert it to constant? We're going to use offset as 0 and use all zeros in here, and then we're going to just make the register already preconditioned to the total of the I times 4 plus the base is what we did. Now take a look at the code again and you can see what I'm saying. It's a very good insight. Actually, you're going to need it in the project. And I think in the real world too, if you're an electrical engineer, you're getting data from an antenna. You're putting data out in a pulse with modulated motor, okay? And you have some pulse train that's turning the motor. You have to know what bits you're sending out. How do we do that? Well, one way is we access some address. This is accessing memory. But in embedded systems, you can also look at the I/O components, and you can send bits out to an I/O device. It makes the motor turn, or makes the LEDs light, and the same thing. So take a look here. If we want to access a certain address, this is converting from index to byte, and then adding the offset. So at that point, T2 is ready to go. We just need a 0, which is great because it has to be a constant. Now Mars lets you type a register number or register name instead of here. You can put a T1 here, but it will convert it to this because the machine can only execute a constant there. Mars will actually convert to this. So I just show you this so you can get more practice manipulating bits and what's an address and what's data and where's memory and other questions. These are good questions for understanding. So here is a cool one. We have n integers stored in consecutive words of memory. The array base is S0 and n, which is the number of words, is in S1. Write a MIPS assembly language program to count the number of zeros. Yeah. So if somebody's giving you a data file or there's an antenna, okay, because it's your job to interface this antenna and you want to know the percentage of the signal which is below some threshold. In this case, the value is 0. There's no signal coming in. You want to add up that percentage. You're going to count the total number of samples that are 0, divide by the total number of samples you saw, and that's the percentage of time that there's no signal. Is that easy? Well, yeah, that's what the specification is. So here we're going to look at the machine code to do this. So first we're going to initialize T0 right to S0. So we're storing T0, it's the same as a move, right? Moving S0 into T0 because we add 0 to it. T0 gets the same value as S0. What's next? We're going to convert from word to byte. So S1, you say what's S1? S1, we're computing, right? S1 is n. So n is 4 times that. This is the index n. It's in C code, right? N is a variable. Multiplying by 4 is the byte equivalent because there's 4 bytes per word. Then we have to add the offset. That's in T1. Once it's in T1, I'm not going to touch it anymore. Okay. And here's another way to execute this with fewer instructions. So I'm going to show you that. So now we're going to initialize T2 as our counter. T2 is counting the number of times we've seen 0 coming from the antenna. Okay. So we're going to start with reading the value from the array. Offset is 0 because we set T0 here is 0. Okay. And then offset, fine. And what we're going to do is we're going to actually add 0 here each time to the next element. This is the limit. We're going to wait until we get T0 equal to T1. So this is the next value we're going to load. And then what? B and E. So we're going to set 0, not 0 is the branch. So T3 is not equal to 0, which is the opposite condition. I'm going to skip the increment because we're supposed to count the number of zeros. So one way to do that is if it's not 0, to skip over the increment, which is happening here. T2 is the count, zeros, T2. So I add 1 to T2 if it is equal to 0, which is what we're supposed to do. Otherwise, I don't add. What do? I increment my counter. So another way to do this is to add 4 each time to your counter. Now you're counting in bytes instead of words. If you add 1, you're counting in words. Then when we go to access memory, you have to convert that word count into a byte address. Or you can just work with bytes and add 4 every time. And branching back up to start. Okay. Remember, in this case, we're basically working with the index as a byte address versus word address. You may ask later, you look at these when you're studying and say, well, why do you add 4 here and you added 1 over there? Because we're just going to add 4 to the address each time, but you have to compare to the limit, which is also in bytes. T1, see, T1 and T0 are going to be compared. They both have to be units of bytes. So we're ready now for looking at the different types of operands that we are covering and add a few new ones. So we're getting better at this. Now we know what addresses are. We can picture in our abstraction what it means and what a pointer is. What is a value? Well, we have unsigned integers, and we're going to talk about today signed integers. Floating point is the next module. We talked about bit strings already. Those are called logical data values. Each bit has a 1 or 0 condition. We want to AND them or OR them or NOR them together. We also have data type of characters. It's a char, right? C-H-A-R in C. And we represent those typically as 8 bits, as a byte. Technically it's 7 bits, but because it's so close to 1 byte, a lot of times we just use 8. You can represent more complex things like different character sets if you add more bits. So Unicode, use 16, and then you can even go much more than that. So what are the bit representations? We need to talk first about signed numbers. Let's do that. Here's a nice table to know, to understand. And we've already talked about this so many times, but now we see it here. This is our bit position number. Each bit has a weight. So it's actually implementing this equation. So x is actually a weighted sum of a coefficient, which is the bit value, 0 or 1, times its position. For example, this is 1 times 2 to the 0, plus 1 times 2 to the 1, plus 0 times 2 to the 2, and 1, 2 to the 3, and nothing else. What is that number? 11. All right. So this is an unsigned number, and here's a table for unsigned binary representations. You don't have to memorize it, but if you look at it this way, you can see, right, anything that has a leading 0 of these 4 bits, just know the 4-bit representation. It's got to be a number less than 8. And then once you know that, you can add 8 to any of these. It's not hard to remember these. Right? Some other things you might remember, like this is 10. It looks like 10. That's 4 bits. See the 11? What about signed integers? So signed integers, we'll look at a few different representations, but they all have something very nice in common. That is, the most significant bit is always 1. There's a procedure to invert the value. You probably learned this in 3342, but we'll cover again as a review. So if you want to go from x to negative x, let's start with a value. Here's x. I want to make negative x. Negative of negative 6 is 6. So how do you get there? Convert this to binary. Is regular 6. Complement the bits, and we get this value. All right. So here's regular 6. You can go the other way, right? Let's go the other way. For 5, we make negative 5. So here's 5. You complement the bits, and you add 1, because it's 2's complement. 2's complement, you complement and add 1. What's 1's complement? 1's complement is just the bit negation. It's a not function. You're going to say, well, why do we have 1's complement and 2's complement and make this complicated? It turns out 2's complement, we can use a regular addition, and we don't have to worry about any types of special cases and testing things. 2's complement has another advantage, that there's only one representation for 0. We'll talk about that. So first of all, this is a procedure to complement signed integers, and this is the table for signed binary. So here's 0 is the middle line. Here's 1, 2, 3. It's the same as the previous table, right? See the 1, 2, 3 here? It's counting up in binary. So positive numbers are the same. Let me say that again. No matter what the representation, if it's 2's complement, 1's complement, even sign magnitude, the positive numbers always look the same. Well, that's good, because it gets rid of half of the guessing, right? The only thing you have to worry about is the negative numbers. That changes if it's 1's complement, 2's complement, or sign magnitude. How does it change? Well, if it's 2's complement, you have to take the number, invert the bits, and add 1. And you can go the other way, doing the same thing. Take the number. 5 is 0, 1, 0, 1. Complement, add 1, and you get negative 5. So you're going to say, is there another way to understand this with maybe not so many, writing so many 1s and 0s? Here's a cool way that I found over the years, is if you think of the number line this way and 0's in the middle. We'll get back to this, but we start with 0. If you go positive or negative, all right, positive is appending 1s going up. Or you add 1, 1 to 0, you get 1. You add another 1, well, is 1 carry 1 is 2, right? Plus 1 is 3. We'll keep adding 1s. So as you want to go negative, you start at 0, and you start subtracting 1s. Well, if you have 0, you have no ones to subtract. So actually, we're borrowing everything. That's what this really means. I'm borrowing. I start with 0, and then I subtract 1. Well, you're in debt. See, that's a lot of debt. Then what? This is the first one is 1. 1 tells us it's negative. You can see this is going to keep going. How many ones do I have to subtract before that most significant one goes away? A whole bunch, right? So the way to remember it is the most significant bit, if it's a signed representation, it turns out it's 1's complement, 2's complement, and sign of magnitude, which we'll show you, has the property, if the most significant bit is a 1, it's a negative number. Do you need to know that? Yeah, you need to know that because we're going to show you some values and you have to tell me if it's positive or negative because you're working with a sensor and an antenna date is coming, and is it positive or negative? Most significant is a 1 is negative. So in this representation, if we have 32 bits to work with, okay, or we have n bits to work with, this gives you an idea of what range of numbers you can represent with 32 bits. If they're signed, it's actually half the range as if they were unsigned. Remember, 2 to the 32 is 4 gig? This is about 2 gig. As a power 2, not a power 10, right? But as a power 2. Okay, is it making sense? Yeah, it makes sense. So, why did I spend all the time? Because I said we need to know number representation. We use 2's complement because it allows us to make for more reason than anything else, it makes the circuit really simple to design. We're going to see that. The 2's complement representation, we don't have to have special negative handling circuit. We just add them as if they're positive numbers, and the sign automatically, magically appears. So, because we have negative numbers, we had something that was like sign extension. We already saw the shift right arithmetic. It preserved the sign. There's other times we need to preserve the sign. So here's an example. There's something called sign extend. We need to preserve the same numeric value, means we don't want to change the sign. So if we start with this value as a positive 2 as 8 bits, you take in a simple sensor. Maybe it's telling you what floor the elevator is on. So you press the button for the 3rd floor, but they also have some check in there, and they're going to send some data back to the simple 8-bit processor that's there that feeds back, yeah, I'm on floor 3. That comes back as an 8-bit value, but inside the processor, what's supposed to be a 32-bit processor, supposed to be a MIPS processor, you have to convert that 8-bit value to 32. Well, if it's a positive number, no problem. If the leading value is a 0, I just extend the leading bit here to make it a 32-bit value. And you're going to say, why would I want to do that? If the sensor is sending you a byte and the processor needs to go into a register as 8 goes to 32 bits, we have to populate the missing bits somehow. If you just put 0, it works fine for positive, but what if coming from the sensor was -2? Is this -2? Yeah, because -1 is what? All 1s. I take away 1, 1, I get this. It's -2. So, suppose we just put all 0s here and convert to 32 bits. Did we convert to 32 bits? No. We changed the sign, right? We need all 1s here. Does everybody see why we need sign extension? Sign extension is needed anytime you want to convert one bit format to another. We can't just always write 0s. If we're in module 3, no problem. When we get to this module, we're working with negative numbers too. Negative numbers need leading 1s. So, what do you need to know? Some instructions extend the immediate value, right, to 32 bits. Like add immediate starts with a 16-bit value. Remember it was constant with 16 bits? But suppose that value is added to something, which is a 32-bit register. We need to extend the sign. So if it's a negative, it's all 1s are filling those other 16 bits. I showed you 8-bit value here. LB is a load byte, which we'll talk about next. Extends the byte value to 32 using this format. Okay. There's also load byte unsigned. There's LB and LBU. This is load byte, and LBU is load byte unsigned. It turns out since ASCII is only 7 bits, if you use LB, it's fine because the first bit is a 0 anyway. LB and LBU for characters, we're going to see in the next slide. Characters, you really only need 7 bits according to the official ASCII, okay? But if you want to do things like kanji, the character set, and flashing and different symbols and things, then you need more bits. So here's the ASCII codes. Every time we type something on our cell phone or we type it on our laptop, if it's a character, it's actually stored using this bit pattern. These are arbitrary, but there's some pattern to these. At the beginning are some control characters, like sounding a bell or making a backspace character. These are non-printable characters. Then we get, starting from 32, okay, decimal 32. Starting from 32, we get a space, and then we get some symbols. They're lumped together, okay? And then we get these digits, start from 48. And you say, why 48? Well, 48 in hex is a nice round number. 48 in decimal sounds strange, but what's 48 in hex? It's how many 16s? Let me say it one time. 48 in decimal in hex is how many 16s? 3. And anything else? No. 3 plus 0 ones is 48. So this is 0 character up through 9 character. Because they're in sequence, we can compare, remember, branch less than, branch greater than. We can start to say, is this, that's our next slide, is this thing a digit or is it a character? Well, I'm going to see what range this character falls in for its code. We have uppercase letters, they start at 65, which is 64 plus 1, because they put the @ sign there for whatever reason, that's what they decided. But 64 is a round number, because it's 4 16s. And then we have lowercase, 127 of them. Okay. So let's look at the instruction to access 8 bits at a time, knowing that it's going to be transferred into a 32-bit register with sign extension. That's a load byte. When do we want to use this? So we're accessing characters of a string. Store byte is the same as store word. It's nothing new. It's the same syntax, but it's going to move 8 bits at a time instead of all 32. So here's the syntax, and then we're going to show you, okay, the actual byte. So here's LB and SB, the syntax. The register, offset, and base is the same as load word. Here's how you represent it as bits. Look up in the table. There's LB has a opcode sequence, 6 bits. The question is a very good one. Which 8 bits get transferred, and transferred from where to where? So the load byte places the byte in memory as the rightmost 8 bits of the destination register. What does it do with the other 24 bits? Sign extends. Okay. And store byte is going the other way. We take the rightmost bits of register and we put it out to memory. What about the other 24 bits? It's going to overwrite them. Okay. Does it change the value? No, it just leaves them intact. So let's make this visible and so you can see it. The diagram's always worth 1,000 words. So here is LB T1, comma 9. Now notice this is not a multiple of 4, okay? So here's our word boundary, word boundary, word boundary. So this is 8, right? Starts the next word, but actually this is just the 9th byte. This is where you can see memory's byte addressable. I've been saying those words and it's just been like Greek, right? But now we can see byte addressing memory. You can access an individual byte of memory even though the word is composed of multiple bytes. If it's a 32-bit word machine, it's 4 bytes, right? 64 more. But here we're accessing, it's byte addressable, we're accessing a single byte. And where does it go? It always goes to the lower 8 bits. What about these upper bits? Sign extend. So if this is most significant bits of 1, then we got all 1s in these upper bytes, which are 8 bits each. This is my last slide for today. I'll let you ask any question.